Yeah, so my name is Matias. I have the pleasure of working with actually many of you here in this is a room on the standard every week. We have a lot of fun on trying to kind of finish it up and tie the spec up, hopefully very soon. And one of the new things in this spec about zone namespaces and ZNS in general is the Zone Append command. And it's kind of it's a new way you want to write to your storage. It's a new way you kind of can architect your system around this new type of functionality. So just to start all over, this has been around for quite a bit. Zone block storage has been in HDDs for the last 5 years or so, and mainly through this called SMR, which is single magnetic recording. And the idea is that you have these hard drive tracks and you kind of write them in overlapping, and that way you can squeeze in more capacity on the hard drive. The thing is, when you do that, you actually have to write sequentially, because these singles have to be lined perfectly next to each other. And that meant that zones came around, so the standardization for zones came into SAC and CPC and SCSI and ITA. And kind of enforcing this, so you kind of have this co-design between the host and the drive, and kind of saying, well, within this zone, you got to write sequentially. And then the cool part is, well, if you then do that, you get the extra capacity, but also you want to communicate to the host when you kind of want to rewrite this zone. So there's kind of semantics in that, and this is kind of a very robust interface that is deployed today at many large storage consumers around the world. So it's quite robust, and the whole Linux stack is very mature at this point. So the question is, why solid-state drives? Why do we want to apply this interface to solid-state drives? So those who've known me for a long time knows that I've been running around talking about open channel SSDs. And all the benefits that we saw from open channel SSDs is actually what we kind of got to go in and say, well, this should be Zoned Namespaces, ZNS, and NVMe. So all that kind of previous work, that's research that was done in the industry, kind of turned into be ZNS today. And no secret is that, well, when I pulled out the spec, created the open channel specs, I kind of looked at SMRs. So kind of derived from that. The only thing I didn't do was to call it zones instead of chunks. But then you did all these kind of different things that we had to do to get it to working for SSDs. And then we kind of figured out this is a bad idea, this is a good idea. It was time for standardization. So that's where we are today. And we've been working on it for, I guess, 16, 18 months now. So we are getting there where it needs to be done. So what do you get from this? So if you look at a typical enterprise SSD, one of the cool parts is that you have tons of over-provisioning. So you have 28% over-provisioning, and that's what you need, so you get good garbage collection performance within the drive. So usually you have 28%. With ZNS, you can just say expose it all. You can even expose negative over-provisioning if you want to. It's kind of a vendor customer kind of discussion. And by that, just by adopting these zones, you actually get 20% more storage capacity for a 28% over-provisioning drive, for example. This is example, so don't hang anyone up on it. This is if you have a consumer drive which have 7% marketing over-provisioning. It's obviously less than 5%. But for those drives, you're not doing heavy writing anyway. So, but still, either way, if you go to consumer drive with 7% or you have 28 with enterprise drives, if you move it to ZNS, you have a full write bandwidth. You have it were a really performant enterprise drive, even if you only have you still have 7% over-provisioning. So what happens is that within the SSD, what happens is that we have a zone. So SSDs are vastly different from hard drives. Hard drives have tracks, and we write sequential within those tracks. SSDs have NAND. And within those NAND dies, we have flash blocks. And those flash blocks need to be written sequentially. And that works out with zones. So now we have the same semantics that applies to original to hard drives, actually also applies to SSDs, but for different reasons, which is the really genuine cool fact about this. So what happens is that we map these zones, and we map them into actually the media, how we manage the SSDs today internally. So we map the zones into flash blocks, so they're aligned perfectly. And why we do that is that normally you would have this garbage collection. Garbage collection inside of an SSD means that you wrote to all these flash blocks, and then at some point you need to garbage collect because you need to find free space. And you go out and say, well, let me find the flash block which have the least active LBAs within those flash blocks. And then those active, before you can actually rewrite it, you have to copy them out, like read them and move them somewhere else. That's the garbage collection process. So that's really expensive. So over here to the right, there's a use case, an example with like RocksDB, where we look at just having this workload where we have 7 billion inserts followed by 5 billion overwrites. And then we measure on the drive side, we measure the write amplification. So a write amp of 1, we're golden, great performance. A write amp of 4 means that for every write that goes into the drive, you're writing 4 times internally in the drive. So if you're able to write 100 megabytes per second, you're actually writing 400 megabytes per second within the drive. That sucks. What this turns out to is that when you have that, that means on NAND media also is that it's really fast to do reads. It takes like 50, 60, 70 microseconds. Writes, that's bad. That's like 2, 4, 5, 6, 7, 8, 10 milliseconds to kind of write to these. And you need to write a bigger granularity. So there's a lot of things where it kind of doesn't turn out because you can only do one at a time. So you can only do one read or one write at a time. One of the cool parts is that originally when we made Open Channel, we were in a world where it wasn't really fast to do what's called erase and program suspend on media. But actually the last couple of years, there's been so much progress on NAND media that today there's a negligent overhead when you actually have to do, for example, a program erase suspend. So together with that, you reduced the write amplification by 4x down to 1x, for example. You're also having these very much improved program erase suspend on the newer generation of NAND media. So all that together kind of makes it very compelling that we apply the Zone interface onto it and kind of get these benefits. So for SMR hard drives, we just got the capacity. That was kind of the improvement. And then you got all the host side work. For SSDs, it's like, where have you been my whole life? This is how I'm supposed to be talked to. And it's kind of, you kind of remove all the cruft, all the things that gave you bad quality of service of the drive, all things that have like all this media that you hide away. So all those things goes away. But there's a fine line to go here because we don't want to go expose all the quirks of media. Like the NAND media, that's hard shit, sorry, hard stuff. And it just keeps every new generation. And when I was young, there was people here in the audience that yelled at me, said, you know, it's not really gonna work out. And I said, yeah, we're gonna do it anyway. And we did, it went on. And then I joined WD, they have their own NAND. It's like, yeah, I see how I got away with it last generation. This generation, I see where you're coming from. So it's starting to get there. At the time, I was like, oh, Fusion IO, you had such a good time. Fusion IO made like a whole side FTL. They had SLC. They were easy stuff. It worked forever. MLC got a little bit hard, but not really too hard. Then TLC and QLC came. QLC, I'm like, I'm just laying flat down. You should not manage that media in any way. Let the drive do it. Not because we don't want to expose it. You can say, give me the drive and expose it. You can build it yourself. But it's because it's a better interface. You don't want to have that communication between the drive and the host, because you need to make decisions in microseconds when you manage these kind of media. So you need to kind of, and if you have to go up and back between the hosts each time, you're wasting a lot of time. So there is a compromise here where you want to find just the right interface on how you talk with these SSDs. You don't want too much, you don't want too little. You want this fine line where you kind of make sure that the host can still do its work, not get overburdened by managing an SSD, while still getting the benefits of data placement and kind of manage that. So that's the fine line that we're trying to walk here with Zoned Namespaces. So this is standardized in NVMe Express. And one of the cool parts is that we can't talk that much about it because it's not public yet. So all here is kind of wiffy-waffy, not really, but just a dance around concepts. That's kind of what we can talk to. We can't talk about how it's really defined, the greedy and needy details, and so on. But this is enough for us to kind of go on with the interface. One of the things I want to say about it is that in SAC and CBC, it's kind of an overlay all onto read and write. So it is an NVM command set. We just put on zones and made these semantics. So we did the write sequentially. And then these zones, we have a namespace. And then you have a namespace that's kind of this, like a normal block device that shows up. and you divide it into fixed size zones. And within the zones, you write sequentially. Obviously, SSDs are not HDDs, as we said before, so, well, we gotta be flexible. We're gonna add some new stuff. Some of the new stuff we added in was zone capacity, because in ZNS we have fixed zone size. If we want to run and use it with Linux, the zone size has to be a power of 2, because that's kind of how you most efficiently implement it on the host side. But the writable capacity is typically different because flash blocks inside the media are never a power of 2. I mean, we can go back to the NAND fabs and tell them, could you please make it a power of 2? Yeah, sure, we'll get the media to you right in 5, 6, 7, 8, 10 years. It's fine. So that's not really an option. So we got to work with it in the meantime. And that means that, well, so now we have this new field called zone capacity, which is the writable capacity within a zone. So this is different from SAC and CPC, where you always have the writable capacity within a zone being the full zone size. The zone descriptors, one large adopter of this that's asked for when you open a zone. I want to put some metadata on. Yeah, because then I can be self-identifying a zone. Well, you can put it in a UID, you can do whatever you want. But that's there, a small bit amount of data you can put in, so when you open a zone, you can kind of put that in together with. And then there's the one we're going to talk about today, which is the Zone Append command. It is the new fun one. All this is soon to be published, very, very soon. But yeah, we'll see when it kind of happens, but hopefully very soon. So just to give you like some visuals on where we are. So we have these zones, and this looks very much like you have it in SAC and CPC. So for those of you who have seen this before, we have these zone states for each zone that says if I'm empty, if there's no writes to it. It says if I'm open, which is implicitly open, explicitly opened. You have something called a closed state, which is for SMR HDDs, maybe something about SMR hard drives that we release some resources. The same applies to these ZNS SSDs. It really depends on the implementation. We have these read-only and offline on the side, which can happen if it's implementation specific, if those can happen at all. Yeah. And then we have, you go to full, that's when your zone is actually fully written. When you write all the writable capacity within the zone, that's written. That's it. Right, so we talked about zone size that's fixed. So down here you have like 512 megabyte zone, and the zone capacity, let's say it's 500 megabyte. So that's the writable capacity within the zone. And then you have X of these zones on an SSD. Cool. So for those of you who would like to kind of say, well, as we go ahead, oh, this is cool, I want to adopt ZNS, yay! Or SMR hard drives. This has been going on for 8 years, like 5 years. Damien, who unfortunately can't be here today, his team and him has been working quite hard on making this into the Linux kernel for the past 5 years. So they have like a full mature storage stack where down the bottom here, what we have is the SCSI HA layer. You have the block layer, which is kind of have been zoned enabled. We have DM zoned, which is kind of if I really didn't want to have like the zone block device and all these weird things where you have to write sequentially within zone, DM zone can make it into a traditional drive with all these glorious overheads that it has, garbage collection and so on. But where it's really cool is that, well, if you have an FTL, you can kind of go ahead and say, well, why the many file systems are like an FTL. So we have F2FS, which has been here for quite a while, support into that. So if a zone device, like a zone block device, you can actually put F2FS on and it works. So we have this working with ZNS and with smart drives and so on. Dio Hero from Damien's team has been working tirelessly to get ButterFS with zone support. So we have multiple patches on the kernel mailing list. It's still not pulled in yet, but it's getting there. XFS, we are still kind of in the planning phase of going forward to. And then we have ZoneFS, which is this new kid on the block, / file system. And that one is a new file system where normally when you talk to an SMR hard drive or a zone block device in general, ZNS, is that you would have to go in and say, communicate to the drive using IOCTLs. Like, give me a report to zones. Well, okay, well, that's an IOCTL. And then you had to very carefully do the write and reads so that they matched it. Very carefully. Don't you do something wrong because the drive will scream at you. Well, okay, that makes it, oh, well, if you've done it a couple of times, this is pretty easy. but let's kind of have some protection training wheels in place and kind of make it up. And while you anyway have protection wheels, well, let's have the benefits of a file system as well. So we can start to do page caching and so on. So Damien has pushed up ZoneFS, which takes a zone block device, the zones, and actually exposes it as a file system. So each zone is a file. That's pretty cool. So I'm going to talk more about that in the next talk, which Damien should have presented. Then upcoming, so the ZNS spec is not public yet. We have all of this code kind of available internally to enable these ZNS drives. The thing is we can't open source it until the ZNS spec is out. So that's all good. So what we've done for the past few months is basically the difference between the patches we have internally and what's outside, we kind of try to minimize it so we kind of can get. So when we get to the closing day, we just drop in the NVMe patch that kind of enables all of this. That's kind of our goal. So a lot of these things are already being pushed upstream. So today we have like 4 or 5 patches. It's not a big deal anymore. One of the fun parts is Zone Append, which we are still like doing fun stuff with and kind of see, well, let's make this into a traditional primitive within the storage stack, both for SAC and CBC drives, but also for, so in general, so it's that the file system can rely on it because it solves a lot of problems. So Hans is working on RocksDB, we're working on Ceph, we're working on MySQL to enable support for that. We have some other projects that we work on internally that we'll announce at some point. So it's quite active. It's really interesting with Ceph is that you both have BlueStore, which is kind of RocksDB for the metadata, and then you have like an extra store for the actual data when you store, when you have a node that stores data in Ceph. And then you have this new project called Crimson, which is kind of Ceph on steroids, which makes it really fast. And those guys are really also looking into, oh, come on, it's fast. You know, they say it's not fast enough, but it's getting there. So that's what kind of Crimson does. And then we're also looking into kind of have ZNS support in that, because ZNS SSDs are fast, and SSDs are generally fast. So we got to be able to kind of make use of all that performance we have. All right, that's the backstory. So Zone Append. Okay, so hard drives, everything is awesome. One write outstanding per zone, because you cannot have multiple outstanding writes. You can, if you know the ordering they're executed in within the SSD, you can do that. In practice, one outstanding write per zone. That's how we're going to roll. So that doesn't really scale. So here's some numbers that says, like, here's the number of writers to a single zone. And then if you have one writer to a single zone, you can do like 500K IOPS. And if you do 2, 4, 3, and 4, well, you drop it down to 300K. All right, that's all kind of lock attention. Hey, can I write? No, you can write. Hey, can I write? Yeah. So, well, we can do better. Well, we can scale it out to write to multiple zones, like 4 zones. Okay, fair enough. And we get a little bit of performance. But the thing is just that we have to lock it and look at it and say, hey, can I please go right ahead here? Can I please go ahead? Alone, that is an overhead. So what Zone Append allows us to do is to kind of say, here's the zone, here's the data. Go ahead and tell me where you wrote it. That's what Zone Append does. So you're kind of what's happening is that we are making Zone Append. I like to, from a file system perspective, it becomes a block allocator. It's a fine-grained block allocator. And each day, I get more and more excited about that interface because it solves a lot of problems. And I'm going to get examples on where we can go with this in the future. So any of you who have written a block allocator in the past for a file system knows that this is hard, really hard. Because you're going to track this free space, you're going to figure out where is the free space, there's these pockets, and if you just go allocate then, and some is freed, you get these small tiny pockets, and how if you then ask for a big amount of space, where you're going to get it. So there's defragmentation and so on. It's really hard. Well, the great thing about Zone Append is that it does one thing, and only that thing that makes it great. So it only works within a sequential write required zone. So it assumes that since we are writing sequentially, well, it's only the write pointer that we have to maintain, which means that we get a write, and you kind of allocate spaces only within that. And since you know you're writing sequentially, it's pretty, you get it for free. You're just like, oh, yeah, that's fine. Here's the data I need to do, and inside of the drive, I just allocated, I wrote it there, which is pretty neat. So what this means is that now you have an interface that allows you to do fine-grained writes to a zone, anyone can write it, not just one application, any application that tells you go right to the zone, you can do it. But it also means that we have this host grain, so now the host only needs to do free space allocation on a zone basis. And so instead of having it on a 4K, for example, now we have it in maybe 256 as a SMR hard drive, or something else for a ZNS hard drive, SSD. Cool. So just to really go down like how it is. So here we have like example is like 32 LBAs zone size, zone capacity is 32 and 24 LBAs, and we have 7 commands. So as we kind of all of it, whenever you issue a zone append command, you're writing to zone use the starting LBA of the zone. That's kind of the identifier. And then you give it the data and how many LBAs that you intend to write. So the first one here, the first command is like 1 LBA, 2 LBAs, 5 LBAs, 8 LBAs, and so on. And then the fourth column is like the assigned LBA from the controller. Then we have, like on the right side, we have the write pointer before the command and the write pointer after the command. So the first command there, command 0, writes 1 LBA. So it goes in here. The assigned LBA that goes back to the host is 0. I wrote it at 0, and since the host knew it wrote 1 LBA, it knows, well, it is 1 LBA. And you can then go ahead, well, I wrote in the second command, well, I wrote 2 LBAs, yeah, and then you get the assigned LBA is 1. But if you look at the write pointer before, yes, it was 1, so that you can kind of see it returns the write pointer before the command was executed. And then you kind of, the write pointer after the command, you don't see that. That's kind of the drive, but it's kind of the internal state. Think of it that way. And then it just keeps kind of going with 8 LBAs, 1 LBA, 5 LBAs, and 2 LBAs. And then when that happens, when you written all the writable capacity on the zone, it transitions to full. Cool. So we have this whole environment around it on how to use it. Where we have NVMe CLI in keys tool. Yeah, there, yes, exactly. We have the zone report, and we can report the zones. So what we did out here to the right is that you say NVMe zone report, you tell it just give me the first zone, and you have the starting LBA with a 0, you have the write pointer, which is 0 at this point. There's the capacity, which I choose to not to tell anything, and then we have the state, which is empty. And then I'll append 1 zone to it, 1 LBA to that zone 0, which the next command is like zone append, and then write to zone 0, write 1 LBA, and that 1 LBA is 4K, and then to this device, success. And then I go read out the zone report again. And there you can see the write pointer increased to 1, and now the zone, since we didn't do an explicit open with the other zone management commands to do, it turns out to be, yeah, implicitly opened. Then we have appending 8 LBAs, and then we get to a write pointer of 9. So this all works today, and kind of we put in the plumbing and so on. So this means you can, obviously that was NVMe CLI, but you can put this into your favorite file system or your distributed file system, wherever you would like, and basically write on that block. So you can go in and say, well, here's the zone start, and here's the block. And then you go in and say, well, zone append, here's the LBA, and then the data and how many LBAs you would like to write. And then you get it back, you say where it is, and then you map it with this chunk below. So that works pretty nicely. And so if we kind of look at how it works within, so that's kind of, this is your very, very simple block allocator. And here it is kind of where, when you submit it down. So there's a new, how we propose to implement it is have this request operation zone append. Actually, Christoph did the first POC of this internally. And we then have set the BI sector, which is what the LBA that goes down to the drive, the zone. We add in the data to this BIO, and we submit it. And then in the bottom here, we get out where this assigned LBA, where it came out on the other side. Cool. So, OK, so there's 3 use cases that I kind of want to mention, where there's RocksDB and ZNS. So this is the work that Hans is working on, and where we have the Zoned Namespace support into RocksDB. The ZNS environment. So the way RocksDB works is that it has these environments, POSIX environment, yeah, and the zone environment. And there's a HDFS environment as well. And what we're the way RocksDB, what RocksDB is a key value store where keys are values, kind of arbitrary byte streams. So and the way it works is this log structured merge tree data structure where you kind of have the hot data in the top and the cold data in the bottom. And what's really cool about this that this RocksDB actually aligns straight to how an FTL would work. It's not how you build a traditional FTL, but it's kind of, you can align these sorted string tables, these SS tables, those blocks, you can actually align them to zones. So you kind of, what happens is that in this particular workload down here, where we had the 7 billion keys filling and then overrode those 7 billion keys, we got to get to like a 5x write amp, and then we plugged in to like a ZNS drive, and we get not straight 1, but very close to 1, which is what we wanted. So Hans has some numbers that says like, yeah, oh, let's not get into that. Yep, we'll get time to present that when we have all the full numbers and kind of got through it. But it's looking very promising, and it's really awesome to see. And this is one of the things that we're kind of planning up to push upstream, up to RocksDB within the next couple of months. It's going to be awesome. OK, so that's one use case, and this is where also Zone Append comes in, because, yeah, you can kind of just leave it and send it off. Really good. The other part is that where this really makes sense is ZNS Append and swap. Normally, when you want to do is that traditional layered approach is you have the swap subsystem, you have the swap file. Swap file is going to be somewhere, going to be on a file system. Then the choice is between a ZNS file system or a file system, you know, the conventional one. And then the ZNS device, yeah, if it's a file system, that's a ZNS enable. Or in the other case, we have ZNS device mapper, that kind of like DM zoned, or something else we're working on called DM SAP, which does the same kind of SSDs. And then the ZNS device. And what we're going to do here over in the other approach is that just take the swap subsystem and make it talk directly with just the ZNS device. And the idea is that you already have the page table that's managed by the host. Well, let's not have, because there's a mapping table within the file system, there's a mapping table within the device mapper potentially. Let's not duplicate that. Let's use the page table that we already have. And the idea here is that we want to actually, when you want to flush out data from this swap subsystem, well, you just send it down to the Zone Append, and it's going to tell you where you wrote it, and then you update the page table. So there's a lot of here log contentions that you can avoid, which is what Adam down there is working on. And I wish to have numbers, but maybe we'll do that next time. To really beg them, can I show, can I show? And we want to make sure that they're perfect. So I'm looking forward to that. All right, the last thing I want to show is, well, so these other 2 years, those for a local system. And, well, if you have a distributed file system, there's no reason that usually if you have Ceph, you have an OSD, and you have an OSD for each node, like each drive in the system, or how you choose to arrange it. And the thing is, well, you can actually, in this scheme, you can have clients actually just, here's a zone on this drive, go write it. You can do that. You don't need to coordinate. The only time you need to coordinate is when, hey, which zone should I write to next? That's what it enables. Obviously, there's more to it. Security model, multi-tenancy, all of that. But if you just don't look at that, here's kind of what it enables is that you have these nodes, and they go talk with this zone allocator in this distributed system and says, well, that's great. You just go ahead and write to this zone. And then these nodes kind of, so what we showed over here is that we have 3 processes, one SSD, P1 to 3, and then P1 is like, hey, give me a new zone. So 0 is returned. P2 does the same. And then P1 and 2 writes, and they get like 0 and 1, they'll be 8 returned, like designed LBAs. You have P3, which also, hey, I want to be in the game too. That's zones. And I get zone 0 too. And then they kind of writes on, so it gets like 2, 3, 4. And then they continue writing until you have no more writes left in that zone. Then you get an error. And then you're like, OK, cool. Then I'll go ahead and fetch a new zone. Right. So there's various optimizations you could do here to the last part. Maybe if you know something that you know you got in the end, well, there's no reason that you try to write next time because there is no capacity. So just go straight ahead. But the other guys who didn't get the notice, get the like, hey, this zone is closed, finished, full. Well, they kind of got into this. But this only has to be done whatever zone size is. So this is a rare event, but it still is there. And if you have a large distributed scale system, this matters. So there's various kind of optimizations we can do in this kind of system. Yeah, so that's kind of a little bit about Zone Append, what kind of options we have. And Christoph says, no, go, stop, which is here. There we go, which is on time. I don't know how long.
We're officially out of time, but I think we'll have time for some more questions and remarks.
And then the expert in the room.
Hi, Ted from Google. So one thing I noticed namespace reclaim. For example, with swap, it's fine that you just constantly append as you swap out, but as you swap back in and things get invalidated, it seems that every single user of Zone Append is going to have to do its own garbage collection. Have you worked on that?
You want to wait for the talk after the next talk.
That's true. We're working on that. We are painfully aware of that. But I wanted to leave you with a very positive thing, that everything is perfect. And then some of you can write very long papers or get gray hair over the next couple of months as you kind of see, oh, there's, yes. And I know Adam can also kind of, talk to it. Thanks, Ted. Yes. Thank you.
Sorry.
No. I like it. Hey.
Hey, Matias, this is Kanchan. I have a question on the Zone Append. If the host is sending a write which is larger than the Zone Append supported by the device, so the host will have to send multiple Zone Append in order to serve that.
Yeah.
And if it sends multiple Zone Append, perhaps they need to be serialized. Or can they go in parallel?
They can go in parallel. Yeah.
But then host is
I know what you're getting.
Host is expecting only one LBA for the entire
so
reason, right?
There is another limit which is sorry, I can't talk about spec. There's another limit that says how far up you get until it kind of breaks up, and the host will have to respect that limit, such that. So yes, if you make it up such and the host kind of breaks it up, you're screwed. Yes. So to do that, you have to follow that's a field, which you see in the spec that kind of defines that, and kind of says, so if you do it, you're all bets are off. Yes. That's the answer.
So another question which is not related to append, but with respect to GNS, do you think it makes sense for MLC and TLC as well?
Yes.
Okay.
There is a benefit for, if you look at QLC, it's really a very few number of writes in this type of media, and the problem is that, there's few writes. So if you use and drop this into an enterprise environment, you don't have a lot of writes, which is a huge problem if you want to use them actually for databases. So that's so you want to use QLC for where you don't have a write-heavy workload, or you have tons of storage and you want to do it anyway. TLC is where it makes a huge amount of sense. So this is database workloads. Have a ton of interest in that. TLC, SLC, all of it makes complete sense. We have, that's a very active topic. So it's ZNS is definitely not for archival storage. It's for high performance because you reduce the write amp. So suddenly the problem you have is that these SSDs, the tail latency blows up on traditional SSDs, so you can't have multi-tenancy. ZNS kind of solves that, such that you maybe don't have to do NVM sets and so on because the performance is good enough.
Thank you.
Peter Desnoyers, Northeastern. Now, for the addresses returned back, I can see how it's sort of very straightforward how you would deal with that at the kernel level, but I would be fascinated to see the user space API to
Yes.
augment your read with something about where it actually went.
Yes.
You're right, sorry.
Yes. So we're extending IOU ring.
Okay.
Oh, and Christoph didn't blink. We're extending IOU ring. Yes, we are doing that. He is okay and now on board. Yes. So IOU ring, then when you do it right and you get it back. So we have that interface. We're also looking at libaio. Didn't flinch either. But IOU ring, I think there's some bits we can use there that Jens kind of left for us to do. We do have prototypes, and we do with Rockspeed, but we kind of have to go. We want to do it upstream so everyone can get the benefits of it. But there's also the other plumbing work. We want to make it a generic interface, so this has to work for SATA and SAS as well.